Right now, it is officially hotter in Tulsa, Oklahoma than it is in the middle of the Arizona desert.
Yeah, which is just wild to think about.
Right. And while the West Coast is breathing this massive sigh of relief, the Pacific Northwest is trapped under a giant smoky sunshade.
It really is a crazy map today.
It is. So today is Friday, August 14th, 2026. We are looking at the National Weather Service's selected city summary via the Daily Tech Reader. And, instead of just reading you a sterile list of temperatures, we are going to map out the massive atmospheric tug of war happening across the United States right at this exact moment.
Because it's an incredibly dynamic snapshot of our climate reality today. I mean, when we analyze these numbers together, they stop being isolated data points, They start revealing a vast, interconnected physical system.
Okay, let's unpack this. Because if you look at the map for this specific Friday, the diversity of what people are experiencing is it's wild.
Absolutely.
Whether you are packing an umbrella in Chicago this morning or, bracing for brutal baking heat in Tulsa or smelling smoke when you walk out your front door in Portland, this deep dive is going to show you exactly how your local weather fits into a massive continental puzzle.
What's fascinating here is how today's data perfectly illustrates the extremes of late summer meteorology. You have this incredible dynamic where one region's dramatic atmospheric relief is directly tied to another region's absolutely punishing heat.
They're a package deal, basically.
Exactly. They are inextricably linked. The atmosphere is a closed system, right? So a massive shift on one side of the continent forces a brutal reaction on the other.
Well, let's start with that relief, because for a huge chunk of the country, today feels like someone finally turned the AC back on.
A massive sigh of relief.
Yeah, I'm talking about California and the Mountain West. We've been seeing extreme heat out there for weeks. But look at the numbers for California's interior today. Sacramento is sitting at a totally comfortable 81 degrees. Fresno is at 89. Both are sunny, but they are running well below the extreme heat we'd normally expect for mid-August.
And the coastal numbers are even more dramatic. San Francisco is checking in at 68 degrees and mostly cloudy. Los Angeles is a mild 80 degrees, and San Diego is at 77.
That sounds amazing, honestly.
Right. The air mass over that entire region is remarkably stable right now.
And it's not just California. The Mountain West is painting this similarly cooler picture. You've got Denver and Colorado Springs both sitting at 84 degrees. Cheyenne is at 80.
Right.
Billings, Montana is all the way down to 73 degrees.
Which is a huge drop.
It is. But this is where I'm getting stuck on the mechanics of it. I mean, we always hear about these heat domes getting entrenched over the West, lasting for weeks, just baking the earth. How does an entire half of the continent just suddenly flip a switch and cool down?
Well, there's a really important historical clue in the text here.
Okay, what is it?
Look at Casper, Wyoming. It's at 83 degrees. And if we look slightly east into the Midwest, Sioux Falls, South Dakota, is at a cool 75 degrees. The report specifically notes that both of these are experiencing cooler conditions directly following, quote, Thursday's heavy rain.
Okay, wait. Thursday's rain, is it all because of that?
That phrase is literally the skeleton key to understanding the entire western half of the map today.
But wait, I'm stuck on the math here. The sun is still hitting the ground in Wyoming and South Dakota with the exact same amount of energy it did yesterday, right?
Yes, the solar radiation is constant.
So where does the heat actually go? Does a rainstorm really have the geographical power to cool down half a continent?
It does, and it comes down to a principle called the latent heat of vaporization.
Latent heat of vaporization. Okay, break that down for me.
So rain isn't just cold water falling from the sky. It fundamentally alters the energy balance at the surface. When heavy precipitation falls, it completely saturates the topsoil. So when the sun comes out the next day, pouring all that solar radiation down onto the Earth, that energy doesn't go into heating up the air.
Wait, so the solar energy is being intercepted?
Intercepted and repurposed.
Yeah.
An enormous amount of that solar radiation is spent doing the physical work of evaporating the moisture left in the ground.
Oh, wow.
It literally takes thermal energy to break the molecular bonds of liquid water and turn it back into water vapor. So all that heat energy that would normally be baking the air, driving the temperature up into the high 90s, is instead being consumed by the evaporation process.
That is fascinating.
It's essentially the Earth sweating to cool itself down.
I love that visual. The ground is literally pulling heat out of the surrounding air to dry itself off.
Exactly.
But how does that localized ground sweating in places like South Dakota and Wyoming translate to a cool day in Sacramento?
That brings us to the fluid dynamics of the atmosphere.
Yeah.
Think of the air above North America like water in a giant shallow bathtub. When you have a massive cooling event in the Mountain West and the plains, driven by this evaporative process, that air becomes denser and heavier, and cold air sinks.
Right. Heat rises, cold sinks.
Exactly. As it sinks, it displaces the air around it, pushing outward in a chain reaction. That dense, stable air cascades down through the valleys and over the plains, pushing the hotter air out of the way.
Making room for itself.
Yep. That brings relief to surrounding areas,
Yeah.
feeding into that drop in temperatures we are seeing all the way down into the interior valleys of California.
Okay, but going back to your bathtub analogy, if you push water to one side of the tub, it has to pile up somewhere else, right?
Right.
The energy doesn't just vanish into the vacuum of space. So
Yeah.
if the West is cooling down and displacing all that hot air, that heat has to go somewhere.
And it does.
Yeah, looking at the middle of the country, it looks like it all piled up to throw a massive, relentless block party right in the center and the south. I mean, let's talk about Texas, Oklahoma, and the Southeast.
Yes. The engine room of today's weather map.
The engine room, and it is roaring today. Texas and Oklahoma are just baking under mostly sunny skies. Dallas and Fort Worth are both sitting at 101 degrees.
Brutal.
Oklahoma City hits 102. But the absolute peak of the heat, the bullseye on the map today, is Tulsa, reaching a staggering 104 degrees.
104. And moving east offers absolutely no reprieve.
Not at all.
The entire southeast is trapped in this mid-90s to near 100-degree range. Baton Rouge is at 98, New Orleans is 96, Tallahassee is 98, and Nashville is 97.
And all sunny, too. But here's where it gets really interesting, because if you tell someone, hey, it's hot in Texas and Louisiana in August, they are going to look at you and say, yeah, water is wet.
Sure, it's expected.
Right. We generally expect the South to be hot, but why should we pay attention to 104 degrees in Tulsa or 98 degrees in Baton Rouge today? What separates your typical, normal summer hot from this specific kind of baking heat we're seeing in the data?
Well, if we connect this to the bigger picture, you have to look at the one crucial word that follows almost all of those temperatures in the report.
Which?
Tulsa, 104, sunny. Oklahoma City, 102, sunny. Dallas, 101, sunny. Baton Rouge, New Orleans, Nashville, all sunny.
Oh, wow. Yeah, there isn't a single cloud mentioned in that entire block of cities.
Not one. And that lack of cloud cover creates a brutal, unrelenting feedback loop. Remember how we just talked about rain acting as an atmospheric reset button in the West?
Yeah, the Earth's sweating.
Right. In the South and the plains today, that button is broken. What you have is a massive high-pressure system parked over the region. High pressure means sinking air.
Okay.
As that air sinks from the upper atmosphere, it compresses and warms, which completely suppresses any cloud formation.
So it's basically a giant invisible lid trapping the region.
A lid made of sinking, warming air. Because there are no clouds to reflect the incoming solar radiation, the sun just continuously bakes the landmass.
With unshielded heat.
Exactly. As the ground heats up, it radiates that thermal energy back into the lower atmosphere. If you're walking to your car in Dallas today, you aren't just feeling the heat of the sun hitting your shoulders. You're feeling the trapped solar radiation radiating back up from the asphalt, straight into your face.
Oh, man, that is miserable.
And the high-pressure lid won't let any of that rising heat escape.
And I'm assuming without recent rain in those specific areas, there's no evaporative cooling either, right?
Precisely. Unlike Casper or Sioux Falls, the topsoil is likely completely dry. So 100% of the sun's energy is going directly into making the air hotter.
Just a completely closed loop.
It is a self-sustaining engine. The hot air wants to rise, the high pressure forces it back down, it compresses, gets hotter, bakes the dry ground even more, and the cycle repeats.
That sounds absolutely suffocating. It's just compounding day over day. But, I mean, eventually that much heat and that much energy has to reach a breaking point, right?
It definitely does.
You can't just keep pumping heat into a sealed cistern forever without something violently snapping.
Nature abhors an imbalance. When you have an environment that is superheated to this degree, the atmospheric tension is immense.
Right.
The moment the superheated air interacts with any form of moisture or a subtle atmospheric boundary, the results go from uncomfortable to explosive.
Which brings us to the regions where that heat is violently colliding with moisture today. Let's look at the desert Southwest and the East Coast.
Two very volatile areas right now.
Yeah, let's start with the Southwest because the contrast here is striking. It's hot, as always, but there is a surprising twist. Las Vegas is at 93 degrees, but with thunderstorms.
Which is unusual.
Very. Tucson is at 96 degrees, also with thunderstorms. And then you have Phoenix at 100 degrees and Yuma at 102, both specifically flagged by the National Weather Service as very hot, with Phoenix also facing possible thunderstorms.
And we are seeing this same volatile mixture happening all up and down the East Coast and into the Midwest. Florida is practically boiling over. Orlando is at 96 with thunderstorms, Tampa 94 with storms. Up the coast, Richmond is 90, and Virginia Beach is 92, both dealing with thunderstorms.
Just heat and storms everywhere.
And over in the Midwest, Omaha hits 91, Des Moines 87, and Chicago 80, all with showers or storms.
You know, it makes me think of dropping ice water onto a sizzling cast iron frying pan.
That's a great analogy.
It's sudden, it's violent, and it generates an incredible amount of steam. You have this completely baked environment, and then you just throw atmospheric moisture right at it.
And this raises an important question, particularly when we look at the desert Southwest. A lot of people hear, rain in the desert, and they instinctively think of relief.
Right, like, oh, finally, Las Vegas is getting a break from the heat.
Exactly. But a thunderstorm in a 100-degree desert or a 96-degree swamp like Orlando radically changes the sensible heat.
Sensible heat meaning how the temperature actually feels to the human body.
Yes. To understand this, we have to look at how the human body regulates its own temperature. We cool ourselves through evaporation. We sweat. The sweat turns to vapor, and that process pulls heat away from our skin.
Just like the wet ground cooling the air in Wyoming.
Exactly the same principle.
Yeah.
But when you introduce sudden monsoonal moisture into Las Vegas or Phoenix, the air becomes completely saturated with water vapor.
So the air is basically full. It can't hold any more water.
Exactly. And because the air is full, your sweat can no longer evaporate. The cooling mechanism completely breaks down.
Oh, wow.
So while the physical thermometer might drop from 105 down to 93 during the storm in Las Vegas, the sensible heat, the heat index, skyrockets.
Because you can't sweat.
You are essentially boiling in your own skin because the environmental humidity has neutralized your body's only defense mechanism. It feels deeply suffocating.
Not to mention the physical danger of the storms themselves. I mean, going back to my sizzling pan analogy, dropping water onto a hot skillet isn't a gentle, quiet process. Things spit and explode.
The physics of a desert thunderstorm are incredibly aggressive. In the Southwest, the lower atmosphere is incredibly dry, even when a storm rolls in overhead.
Okay.
When rain falls from a high thunderstorm cloud, a massive amount of that liquid evaporates before it even hits the ground.
Because it's falling through a furnace.
Precisely. And just as evaporation cools the ground, this mid-air evaporation cools the air inside the storm column incredibly rapidly.
And cold air sinks, like you said earlier.
Right. That cold air becomes exceptionally dense and heavy. It plummets toward the earth like a concrete block, hitting the ground and spreading out in all directions.
Wow.
Meteorologists call this a microburst. It creates violent, unpredictable winds that can snap trees and endanger aircraft.
That's terrifying.
So this collision of heat and moisture isn't just physically uncomfortable. It creates highly volatile, hazardous conditions for anyone caught outside, whether you are in Tucson or Tampa. The atmosphere is literally throwing its weight around.
It really paints a picture of a continent at war with itself today. You have the cool, dense air cascading out of the west, the relentless, invisible lid trapping the heat dome in the south, and these explosive battlegrounds of heat and moisture in the southwest and east.
It's chaotic.
It really is. But there is one more region we need to look at, and they are dealing with an entirely different, much quieter atmospheric intruder. Let's look at the Pacific Northwest.
The wild card in today's summary.
Totally the wild card. We just talked about how sinking, stagnant air creates a clear, sunny heat dome in the south. Well, that exact same atmospheric stagnation seems to be happening in the Pacific Northwest right now, but instead of just trapping heat, it's trapping something you can actually see.
Right.
The NWS report shows a mix of partly cloudy skies and highs in the low to mid 80s, but it specifically calls out smoke.
Smoke.
Yeah, Portland, Oregon is sitting at 84 degrees, and Yakima and Pendleton and Washington are at 87 and 86 respectively.
Yeah.
All explicitly noted as having smoke or smoky conditions.
Meanwhile, just a bit further north.
Yeah, Seattle is 80 degrees and sunny, and Spokane is 82 and sunny.
The geographic contrast there is stark. It highlights how incredibly localized these atmospheric intrusions can be. A 2-hour drive separates clear skies from a dangerous haze.
So what does this all mean? Imagine stepping outside your front door in Portland today. It's a mid-80s day, which should be beautiful, but instead of those crisp, clear Pacific Northwest skies, The horizon is just obscured by this thick gray haze.
The sun probably looks like a dull orange disk.
Exactly. But I'm curious about the data itself. Does smoke actually function as a weather variable, or is it just like a visual byproduct of a fire happening somewhere else?
That is the crucial distinction to make. Smoke isn't just passive scenery floating in the air. It acts as an active, highly disruptive weather variable.
Wait, really? How?
When you have a massive influx of particulate matter from wildfires, it fundamentally alters the local microclimate through something called the albedo effect.
The albedo effect. How does that work in this context?
Well, albedo is basically a measurement of how much sunlight a surface reflects versus how much it absorbs. Think of wearing a black t-shirt versus a white t-shirt on a sunny day.
Okay, the black shirt absorbs the solar radiation and makes you hot. The white shirt reflects it and keeps you cooler.
Exactly. When a thick layer of smoke settles over a city, all those tiny particles of ash and soot in the upper atmosphere act like a giant white t-shirt for the entire region.
Oh, wow.
They are highly effective at scattering and reflecting incoming solar radiation back out into space before it can ever reach the ground.
So it's basically acting like a giant artificial sunshade over Portland and Yakima.
A very dangerous sunshade. Because the smoke is blocking a significant percentage of the sun's energy, it actually acts as a cap on local temperatures.
Really? So the temperature is actually lower than it should be?
Yep. If a strong wind were to sweep through and clear the smoke out of Portland later this afternoon, that 84-degree high could easily spike into the low or mid-90s. The smoke is artificially suppressing the temperature on the thermometer.
Wow. So the weather report saying 84 degrees and smoky is almost deceptive. It sounds like a somewhat mild summer day, but it's actually a stifling, stagnant environment where the air quality is secretly dangerous.
It is a grim atmospheric trade-off. You might get a slight numerical reprieve from the extreme heat, but you are trading it for severe air quality impacts.
Which is terrible for your health.
Extremely. Those particulates are microscopic, small enough to bypass the body's natural defenses and enter the human bloodstream. And what makes it worse is the physical mechanics trapping it there.
What do you mean?
The weather patterns that allow smoke to settle over a valley city like Portland or Yakima are usually characterized by stable, sinking air masses with very little wind. Sound familiar?
Oh, it's the exact same high-pressure lid mechanism we saw baking Texas, just applied to a different geography.
Yes, and that lid traps the smoke at ground level for days at a time. It's a very quiet, very insidious kind of atmospheric hazard, completely different from the explosive thunderstorms in Florida or the roaring heat engine in Oklahoma.
It really puts into perspective how localized and complex the physical reality of the weather is on any given day.
It's all connected, but experienced so differently.
Yeah. So to bring this all together, we've traveled across the entire map of the U.S. on this Friday, August 14th, 2026.
Quite the road trip.
Right. We started with the cool evaporative relief of California and the Mountain West. You know, the ground sweating, cooling the air, and sending dense relief cascading outward.
The atmospheric reset button.
Yeah. Then we moved into the 104-degree cloudless heat engine parked over Tulsa, where a high-pressure lid is trapping solar radiation against the asphalt.
The broken button.
Exactly. Then we watch that relentless heat violently collide with moisture to create suffocating, stormy battlegrounds in the desert southwest and Florida.
Where saturated air neutralizes our ability to sweat and microbursts slam into the earth.
And finally, we looked at the Pacific Northwest, where stagnant air is trapping a giant smoky sunshade that is literally rewriting the daily high temperatures.
It's a massive, intricately balanced machine. Every single localized event is a gear turning another gear somewhere else.
And this is exactly why taking a deep dive into these numbers matters. I mean, understanding these interconnected physical dynamics, how a wet field in South Dakota can physically push cooler air toward Wyoming, or how the albedo effect of smoke artificially cools a city in Oregon, it's the ultimate shortcut to being well-informed.
It's so much more than just numbers on a screen.
It really is, because this isn't just weather trivia. These invisible physical realities are what determine the massive strain on our regional power grids today, the stress on agriculture, and the literal breathability of the air for hundreds of millions of people just stepping out their doors.
It dictates the parameters of daily human life. But before we finish unpacking today's map, there is one final lingering anomaly in the NWS report that I think is worth chewing on.
Oh. What stands out to you?
Look at the exact phrasing of the official alerts. The National Weather Service specifically flagged Phoenix at 100 degrees and Yuma at 102 degrees with a distinct warning text.
Very hot. Okay, very hot. Makes sense for 100 degrees.
Right. But if you look over at the Texas and Oklahoma data, Tulsa is sitting at an astonishing 104 degrees, and Dallas is at 101. Yet there is absolutely no such flag in the report for them. They are just passively listed as sunny.
Oh, wow. That's a really sharp observation. 104 degrees in Tulsa is objectively hotter than 100 degrees in Phoenix.
Thermodynamically, yes.
So why doesn't Tulsa get the very hot warning label?
And that is exactly the question I want to leave everyone with. How do regional climatological baselines, humidity profiles, and historical data shape not just what the physical temperature is, but how our official systems decide to warn us about it?
Right, because heat is relative to what a city is used to.
Exactly. When does extreme heat go from being a regular, accepted occurrence to an official hazard? And how much of that is based on the hard physics of the atmosphere versus human perception and local policy? It's a fascinating layer of human decision-making placed right on top of the raw meteorological data.
That is such a compelling point. It really highlights that while the thermometer just reads a raw number, we are the ones who have to decide what that number actually means for our survival.
We give the numbers meaning.
Yeah, there's always a subjective human element in how we categorize nature. Well, thank you for taking this journey across the map with us today. Keep looking closely at the data, stay curious, stay cool, and keep exploring the fascinating, invisible forces shaping the world outside your window on this Friday morning. Until next time.